All right. Good evening, everybody. Welcome back. I hope you all had a very good spring break. First things first, if you can hear me all right, I want you to raise your hand. Okay. Good. So I see that most of you are able to hear. So you can go ahead and lower your hand now. Okay. Now, what I will do is, in order to keep the class interactive, I'm going to pick on some of you here. So I only ask, I request that you be willing to unmute yourself and ask any questions that you may have. And uh, also be willing to answer my questions, okay? If I have some questions in the class. Now, any comments about the Cadence project?
So the assignment 3 is the last cadence project, or will we have more?
The idea initially was to have 2 more assignments, but depending on your feedback, I want to see if you guys want more cadence projects for grade, or if you're all open to making them an optional assignment. How is the speed when you're working from home?
We just figured out that's like when we log in, like do the remote control to Hydra be faster than we do through the mobile extern on R.
Okay.
Yeah,
I
on
guess
ours.
there is some issue with that remote connection. It keeps shutting down frequently, and
Okay.
It logs off automatically, Professor.
Same happens. Same here.
Okay, so if that is the case, and I understand it is, I keep getting kick because of Comcast, very slow. I understand. It seems there is a pervasive sentiment that the cadence is painfully slow, and I'm familiar with that. I tried logging in a bunch of different times over the years. But it seems it's painfully slow. So if you're all okay, I would want to go ahead. I will want to go ahead and make the second project um, optional.
Like extra credit?
Sure, we can make it extra credit if everybody uh, is on board. Any no to that, please? Anybody oppose that idea?
Is this still a group project?
It was supposed to be a group project. The second project was supposed to be a group project. We can still leave it a group project, or if you want, it'll be better if you work on it by yourself. I like Brian Ellie's comment. I oppose anyone who opposes that idea. All right. So, second cadence project is going to be extra credit, and then I strongly encourage you to work on it by yourself. If you want to team up with a buddy, that's fine too. It's mostly for your edification and for your practice. Um, in the previous semesters, the second project was usually the most rigorous, intensive one, but this semester I want to ease on that requirement, taking into account the prevailing COVID situation. Now, one thing that you want to pay attention to is when your system suddenly shuts down on you. When you log back in, there may be some lock files. If you're seeing that your system is painfully slow, that is probably because there is some cds.lck or some kind of lock files um, lingering in your account. So there's a way to do that. Um, I'm going to give you a hint on how to clear all log files. And this is what you want to do for the first time. Each time you log into your system, and after you do CDS6 or whatever command you use to invoke your Cadence tools, you exit the command interpreter window, the CIW window, the horizontal window that shows up usually the first time. So what you do is you have to do in the top directory, in your home directory, do CLS admin tool, okay, plus enter. And this has to be, the capitalization has to be exact. Okay, CLS admin tool. So this takes you to an administrative tool with some prompt that looks like this. So what you will do is ALE space dot and then enter. So what you're doing is you are listing all edit logs in the home directory and below. Okay, so it will take a couple of minutes and give you a list of all the old log files that are clogging up your system. So in order to release that, what you would do is ARE space dot. It's going to, all edit logs will be released if you do that command. And you may see the system going a little faster. What I'm going to do is actually type this in the chat window for those of you who want to, followed by ALE followed by ARE. So you'll see that some of the edit logs will be removed. You'll see a message to that. Then you can do an exit. That way you're coming out of this CLS admin environment. Okay, so these are these are certain steps that can help you make your Cadence more responsive and quick. Okay, so that's about Cadence project. Today or tomorrow, perhaps, the TA is going to make some announcement sometime this week about the upcoming extra credit project. Okay, questions? Okay. Okay, so the natural fallout of this, the natural downside of this is that even if the number of quizzes, midterm, and the final exam, because they're not going to increase or decrease, they're going to remain the same. They're going to carry that much more weight towards your final grade. Okay, so I look into what option works best for everybody in terms of considering the single cadence project worth all the 25%, or to distribute the remaining 25% among quizzes, midterms, and finals. So I'll make this decision about as to how to assign this 25%. 12.5% actually. The first project was worth 12.5%. So the second cadence project is worth 12.5%. How do I distribute it? Do I assign it to the old cadence project, or do I distribute it between the other assessment methods? That I'm going to decide based on what is best for a large percentage of the class. Okay. All right, any other questions, please? Okay, so we'll go ahead and get started. And like I mentioned, I ask that you be willing to participate in discussion. If you have questions, feel free to ask those questions. And if you have some comments, they will be helpful if you bring them up in the class. Okay, so now before the midterm exam, we were looking at combinational circuits. Okay, we looked at how to implement CMOS logic, the idea of pass transistors, looked at how the fabrication is done, okay, and then how that relates to the layout of our Cadence project. Okay, so in addition to that, we also looked at the power and delay considerations. As a part of your Cadence project, you have been exposed to different models, higher order models. We looked at the IV, the very basic long channel model that is used for hand design, that is used on pen and paper designs. But then you were using TSMC provided models. Models provided by TSMC for their 180 nanometer technology. These are pretty advanced BSIM 3v3 or BSIM 4 level models. Now, we also looked at the basic modeling for IV characteristics of MOSFET. Okay, so in addition to power delay, we looked at dynamic logic circuits. And the idea of dynamic logic circuits was that there's a cap actually storing charge. Sometimes it is left floating. Okay, and the other main characteristic of dynamic logic circuit is that it is operated by a clock. Okay, so these are kind of the big topics that we discussed in the class before the midterm. Okay, and by definition, okay, combinational logic is defined as an architecture where the output is a function of the current inputs. What the previous inputs were does not matter. Okay, now we are going to look at sequential logic. Sequential logic circuits where the output depends, let's call this function 1. It's a function, the output is a function of the current and also past inputs. Okay, that's the idea of sequential circuits. And in order to capture this notion of previous inputs, there is what is known as states. There's a current state, previous state, and the next state. Okay, all of these states are nothing but some representation of the previous or next inputs. Okay, in order to capture the idea, a concrete idea of past inputs, we use states that represent the codified essence of the previous states. Okay, and then of course there are the current inputs. So when you see states, you have to understand that they are a manifestation of what the previous inputs had been. Okay, so that's the idea. Sequential circuits, the output depends on the current inputs and the previous inputs. It requires separating previous, current, and future states. So there are these 3 states: the current state, there's a previous state, and the next state. So we want to have some mechanism to temporarily separate them. Or meaning at t equals to 0, there was t state 0. At t equals to 1, there is state 1. And at t equals to 2, there is state 3. So we have to clearly define the timing, okay, associated with each of these states. And that can be orchestrated using clocks and using what are known as sequencing elements, okay? So mostly we will be looking at two kinds of sequencing elements. We'll be looking at two building blocks of sequential circuits, a latch and a flip-flop. Okay, so the Cadence project is going to be designing one of the building blocks among other things. Okay, to build the sequential circuits that I ask you to build in the second project, your basic building block will be a flip-flop. Okay. I'm going to discuss its construction here, how it is built out of PMOS and NMOS transistors. Okay. Okay. So we'll know some of the basics. Let me quickly brush up the basics relating to latches and flip-flops here. Okay, but before we move on, let me talk about the idea of static versus dynamic. Did we talk about this difference already? And if we did, in what context? In what context did we talk about static versus dynamic?
Did we talk about this in the power consumption problem?
We did, of course, yeah. Static power consumption and dynamic power consumption. Sure, when the circuit is not performing any useful work, that's static power consumption. And when the circuit is switching on and off, that is dynamic power consumption. Sure, what else?
And for the static, we were talking about that the pull-up network and the pull-down network, it's on just one at a time.
Correct. The conventional regular CMOS that we saw, the pull-up and pull-down network, we called it as a static network, right? And then the dynamic logic circuits, there was just one PMOS plus the pull-down network. And then fundamentally, there was an additional NMOS, of course, plus NMOS. And then there was the clock, and there is the capacitance, okay? In the context of static CMOS versus dynamic CMOS, I mentioned that dynamic logic circuits have a clock and dynamic logic circuits have a capacitance. Okay, so more or less something very similar applies here. The capacitance is usually floating. For some part of the time during the evaluate phase, okay, when the for some under certain conditions during the evaluate phase, the capacitance, not the clock, but the capacitance could be floating. Okay, so this is a characteristic. There is no feedback in the circuit, and then sometimes the capacitance can be floating. Okay, if there were a capacitance here, if there were a load cap here, that would always be connected to VDD or ground. Okay, at any given time, it's either connected to the upper power supply or it's connected to the lower power supply. It's not floating. But the characteristic, the defining characteristic of dynamic logic circuit is that it does not have a feedback. There is no feedback, okay? And it has, sometimes it may have a floating output, okay? For now, park this information to one side of your brain, we will come back and revisit this information. Okay, so it's going to be useful when I talk about the design of latches. Okay, for now, just park it to one side. Okay, sequencing elements can be static or dynamic. So the latches that I'm going to show you are going to be static or dynamic. Okay, and I mentioned we are going to look at two. So give me 1 second here. So I kind of, because of the spring break, I kind of lost the habit. So this is the 3 p.m. section. Okay, very good. Now let's continue. I said there are two building blocks of sequential circuits. They are a latch and a flip-flop. Okay, I'm going to draw both of them, the symbols for both of them. Okay, so this is a latch. Okay, the latch has one D input and one Q output. So the input is D. Okay, the output is Q. Okay, and then there is a clock input. Okay, the flip-flop is also very similar and quite different in the sense that one is edge triggered and the other is level triggered. So I indicate that using the triangle here to mean that it is a flip-flop and that this is edge triggered. So this should be familiar information to us. Okay, this is level triggered. Okay, and I'm going to review what it means by looking at the output waveform. Okay, so let us first understand that both of these sequencing elements have 3 terminals. Okay, there is an input terminal D. Okay, there is an output terminal Q, and then there is a clock terminal. Okay, sequencing elements have a clock signal, right? So clock signal. So these are the 3 terminals associated. Okay, now let's look at the operation of a latch. Okay, the latch itself has 2 states. It has a transparent phase when the clock equals to 1. When the clock is 1, okay, then the output is going to follow the input. Okay, so the latch acts as a buffer. Okay, when the clock is 1. And when the clock is 0, okay, then that state is opaque, okay, independent of what is on the input. Independent of what is on the input, don't care. The output is always going to hold on. The output is going to hold on to the previous value. Or in other words, you can say Q next equals to Q. Okay, the next state will be the current state will continue. Okay, there are 2 conditions. When the clock is 0, the latch is going to behave as an opaque latch. When the clock is 1, it's going to be transparent, meaning the output is going to be copied onto the input. So even if D changes, Q will hold on to the previous value, even if the input changes up or down. Okay, so this is a level triggered. Okay, this is a level triggered sequential element. Now let's look at a flip-flop. Flip-flop is edge triggered. Okay, flip-flop is edge triggered. It copies Q or a D to Q. Let me say copies. It copies the value of D to Q on the rising edge. For a positive edge triggered flip-flop on the rising edge of a clock. Okay, and ignores, and more importantly, it ignores, so this flip-flop ignores changes of D, okay, ignores D at all other times. So let me show you, let me illustrate that using the timing diagram here. Let's say here is the clock. Okay, let's say this is the clock. Let's say I have a clock that looks like this. I'm going to call it clock. Okay, and let's say the input D looks like so, and the same input is applied to both the flip-flop and the latch. Okay, let's say that's the case, and then somewhere in here, the input changes from that to that. So here is D, this is the input. And this is the same input to the latch and the flip-flop as well, okay? Now, let us see how the latch output is going to look, okay? The output of the latch is going to follow, the output of the latch is going to follow the D whenever the value of, let me see, let me pick this value here. So when the value of clock is 1, the value of output is copied onto the input. Or I'm sorry, the value of the input is copied onto the output of the latch. Okay, the value of the input is copied onto the latch, but it just happens after a little bit of a delay. Okay, so the input was this, the output on the latch is going to be delayed by a little amount. Okay, and then this transition on the value of the input is also going to be duplicated, is also going to show up on the output. Okay, because the value of input is 1. Okay, so because the clock value is 1, okay, because the clock value is 1, whatever value change happens on D, it's going to be copied onto the value of Q, onto the output. Okay, that's the idea of a latch, and I'll contrast it with a flip-flop, which is only level triggered. Okay, so when the value, as far as a latch is concerned, when the value of clock is 1, it looks at the value of D, okay, throughout this time. If D changes, that's going to be copied over, okay, after a certain delay. Okay, so this delay is called D to Q delay, because this is also called Q. Okay, this is also called D to Q delay. Okay, that's the idea. Now, there's also clock to Q delay that I have not shown here. I can show it later at a later time. Let's look at the output of a flip-flop. Okay, both of these, by the way, begin with unknown state. Okay, until here, it is unknown, uninitialized. Okay, until the value changes, it's all uninitialized state. Okay, unknown. Now, let's look at the value, how the output of flip-flop is going to look. Okay, the value, the way flip-flop operates is, okay, the value of the input is sampled on the rising edge of a clock. There's a rising edge of a clock here. Okay, at that instant of time, the value of the input is sampled. Okay, the same here as well. At the rising edge of this clock, the value of the input is sampled. Okay, so if I were to change, let's see if I can change this a little bit, just to illustrate the idea of this guy changing. Okay, let's say that's the D input shown in red. Okay, I'll plot the Q value again later, but let's see how the value of flip-flop is going to be. Okay, the flip-flop is going to change at that instant of time plus some delay. Okay, so the value sampled at this instant of time is 0, so it continues to be 0 until the next sample, where the input turns out to be 1. So at this instant of time, the sampled value of input is 1. So after some delay, the flip-flop goes to 1. Okay, so here is the output of a flip-flop. Okay, this is the output of a flip-flop. And let's try to plot the output of the latch here. Okay, so the latch operates on the level. Okay, as long as the value of the clock is 1. Okay, at this instant of time, the value of clock goes to 1. So after some delay, the flip-flop, the latch begins to follow. Okay, this input. Now also at this time, at this instant of time, the clock went to 0. So after some delay, this guy follows as well. Okay, not the flip-flop though. Okay, the flip-flop continues to be 1 until the next clock cycle, until the next rising edge, at which time, if the input is 0, then the flip-flop goes down to 0. So that's the idea of edge triggered and level triggered. Okay, what we have to see, the blue line is only responding to the value of input on the rising edge of a clock. Okay, the value of the input is sampled there, and that is copied onto the output. So if you naturally, there is some delay between the positive edge of a clock and when the flip-flop output changes. So this is called T, clock to Q. Okay, now the same is also applicable in a latch. The latch, there is a delay between the clock edge, T clock, and if there is a change in the output, the delay. So a latch has T clock to Q delay, and also T Q or T D to Q delay, D to Q delay. So here is a question coming up for you. Pay attention. For the flip-flop, the only delay that is of interest to me is T clock to Q. Okay, who can tell me why there is no D to Q delay? This guy is absent in flip-flop. And why is that case?
Because it's low,
Because it is what?
zero, low state.
Because it is
Low,
edge triggered. So unless it is
because
triggered
it
by
is
an
edge
edge,
trigger. Correct. So the flip-flop is always responding only on the positive edge of a clock. Okay. Latch, on the other hand, if you think about it, is responding to the positive edge of a clock and also the level. If the input changes, okay, let's say if the input changes here, from 1 to 0, okay, during the middle of this clock, and there is no edge, okay, even then, in response to the input changing, the flip-flop, the latch is going to change, okay? The latch is going to change in response to change in the input. So there is a T, data, to Q, okay? But the flip-flop never responds to change in data. It only responds to change in clock. And depending on the value of the input at that time, flip-flop may or may not change value. So owing to the fact that flip-flop is edge triggered, it responds only to positive or negative edges and never to data. And that's the reason why D time D to Q is not relevant in flip-flops. Flip-flops are edge triggered. Latches are both edge and level. They're level triggered fundamentally. All right, questions, please. Okay, so what I'm going to do is I'm going to define a few terms. I'm going to give you a few terms and then later talk about those. Okay, I'm just going to name a few terms. We know these actually as a matter of fact. TPD is the logic or the combinational propagation delay. Okay, TPD is the logic propagation delay. TCD is the logic contamination delay. Okay, so let's see, let's pick somebody here to tell me the difference between propagation and contamination delays. Rafael? Rafael Martinez, are you with us? Okay, the next time you log into the class, I want you to make sure that, okay, I think he's chatting something in the window here. Now, I want you to make sure that your microphones are working because that's one way for me to make sure you're attending the class and to assign attendance to you. Okay, anybody else who wants to tell me quickly, it's just a 1 second way to tell me the difference. Okay.
Logic propagation
Yes.
delay is regards to the worst case scenario.
Yes.
And where is what I remember. And for contamination delay is when you have yes, this is the best with the cases.
Yes, that is when every path in the parallel networks they are on. That is correct. Their best case, and I think Brian Ellie also has the same answer as well. That is correct. So propagation delay is worst case, and contamination delay is the best case. We know that. We know that from previous classes. Okay. So, and I just mentioned there is a T propagation clock to Q that is applicable for a latch and for a flip-flop. Okay, so there is a to Q propagation delay. Okay, clock to Q propagation delay. And then I can also do TCCQ, which is applicable for a latch and a flip-flop as well. This is clock to Q contamination delay. Okay, what is the best case delay for this? There is a delay between the clock edge and the output of a flip-flop changing. The same here as well. It's the same. So that's the that's the latch. Okay, the same delay is applicable here as well. The clock edge to when the Q changes. So this is the Q, right? Both of these are Q for flip-flop and Q for latches. Okay, so this delay is T clock to Q. Okay, for a flip-flop, and this one is for a latch. Okay, so clock Q to Q, C to Q for a latch, clock to Q. Now TPDQ and TCDQ, these are the delays that are associated only with a latch. Okay, and their propagation and contamination delay from data to output. Okay, D is always the input and Q is always the output. Input data. Okay, this is clock. One of these is clock. Okay, and the other is of course the output. Okay, clock to the time difference between clock changing and the output changing. Okay, so in addition to that, in addition to TPDQ and TCDQ, these flip-flops actually have what is known as setup time and T hold. Okay, and we are going to look at the definitions of these and the expressions for the maximum and clock frequency that we can achieve, the setup based on the setup time. Okay, there can be strict timing constraints, max and minimum timing constraints. And I'm going to talk about that in the next class. Okay, it's going to, I'll give you an example, a real life example, which can be used for understanding the difference between the setup time violation, hold time violation, and what it entails. Okay, for now, what I'm going to do is I'm more interested in giving you the design for flip-flops and latches. Okay, so far all I have done is I have just shown you the graphs for the clock, the timing diagram for a clock. Okay, and if an input happens to be in this fashion, how is the clock output going? How is the output of the latch going to be? And how is the output of a flip-flop going to be as shown? And all the different delays associated. That's what I have done. That's all I have done. Okay, now what I'm going to do is design of latches and flip-flops. Okay, latches and flip-flops, and you know, you should be able to recognize when you see this. Let's implement flip-flops using CMOS. Okay, using NMOS and PMOS transistors. CMOS latches. And we have gone over this a million times. The transistor here, the NMOS transistor with the source, drain, and gate terminals acts as the most basic fundamental latch. Okay, what is this? Does anybody remember what this is and what the problems associated with this are?
high frequency shorts between the gate and drain?
Yes, there is a clock feed through. If you remember, there were different problems associated with this pass transistor. So this is a pass transistor, right? And there are a bunch of problems associated. There is a clock feed through, there is a channel charge injection, there is input dependent phase shift, non-zero on resistance, so on and so forth. But the first and foremost thing is to note that this is NMOS transistor. So it passes. So let me identify the problems in this. And then the next circuits are all going to step by step solve those problems. Output, the first problem is the output does not swing. From rail to rail. Okay, if that's the output, if I call this guy as the output and this guy as the input, let's say that's the input over here, and the output is on the drain of the NMOS transistor, what is the maximum output here?
Oh, can you hear me? No,
Yes.
VDD minus 1 threshold voltage.
Thank you, VDD minus 1 threshold voltage, because this is NMOS transistor, it passes a bad one. So the maximum output voltage that this can supply is VDD minus VTH. So this does not swing, or the output does not swing all the way from VDD to ground, but the maximum output is VDD minus 1 threshold. Okay, so that's the first problem. Let's look at the second problem. The second problem is the output is dynamic. Okay, the output is dynamic, meaning here is the, think about this, and I'm going to erase this part over here. Okay, let's say I place a capacitance on this output node. Okay, what happens when the gate, which is connected to the clock, equals to 1? When the clock equals to 1, the output on this guy, the Vout, is equals to the input that I apply on the source, Vs. Okay, so this acts as a, so the output is same as the input, it acts as a transparent latch. Okay, so because this switch is on, the input is going to pass to the capacitance over there. The problem happens when this value becomes a 0. When this clock becomes a 0, what happens to the output? Well, the output is not being driven by anything, it's simply floating. Okay, so that's the idea of dynamic. Okay, when the clock is 0, what happens is the output is floating, it's not driven by any value. Okay, the output is dynamic, meaning when VG, which is same as the clock, when the clock value is 0, then Vout is floating. And that's the meaning of dynamic. And I promised you that we were going to come back to this notion of dynamic circuit. Okay, so let me go back there and see what I mentioned about dynamic circuits. Okay, I mentioned that there is a capacitance, and when the capacitance is floating, then I call this circuit a dynamic. And sure enough, when I come back here, the capacitance is floating when the VG value is 0. And that's the reason why it's dynamic output. Okay, capacitance is floating. So what is wrong? What happens if the capacitance is floating though? I'm kind of listing that as a problem here, right? Limitations. Limitations of this guy as a latch. Okay, the input is applied here. The output is taken there. when the clock is 1, output follows the input, so that's a transparent latch. When the clock is 0, the value that I leave here, the value that it is stored on the capacitance, it should ideally be holding that charge, and therefore I have the state holding on to its previous value. Okay, so but what is problem if the capacitance is floating?
Does it tend to leak?
It tends to leak. Think of a capacitance as a bucket, okay, that can hold water. Okay, not just a bucket. All capacitances are leaky buckets with some holes in them. So when you charge it to full and leave it for some time, it's eventually going to leak all of its charge. And while you expect it to be full, it tends towards 0. Okay, so that's the problem. If it is floating, if it is not driven by anything, it eventually gradually leaks its charge. So that's a limitation for us. So let's look at the third problem. The third problem happens when clock equals to 1. When the clock equals to 1, the input is driving. So this applies actually regardless, okay, regardless of whether this is 1 or 0. Okay, input drives diffusion terminal. What are the diffusion terminals in the MOSFET transistor? There are 2 diffusion terminals, right? Remember we were talking about,
Yes, I believe
yes,
the drain and source.
the drain and source are called the diffusion regions. Remember when we were looking at the RC delay model, I mentioned that the capacitance on the gate is C, and each of the diffusion terminals, the source and drain, each of them has a capacitance of C themselves. Okay, so diffusion terminals mean source and drain. Okay, when the input drives the diffusion terminal, which is this guy, source terminal of a MOSFET transistor, any noise that is present on this will eventually be coupled onto the output. Okay, so that's the problem. That doesn't happen when the input is driving the clock, the gate. Okay, for example, when you were doing an inverter that looks like this, the input was driving the gates. Okay, then any noise on the input is mostly not passed onto the output. Okay, so this is more resistant to noise, while on the other hand, this guy, okay, I don't want the input to be directly driving the source or drain terminals. Okay, so input drives diffusion terminal. So problem happens. Noise issues, hard to model delays. There are noise issues. Okay, and then the fourth problem of using a pass transistor. Okay, the fourth problem of using a pass transistor as a latch. Okay, is that the output terminal, the state node, what is known as the state node, is exposed. So in other words, the state node here, the output node here is exposed to the capacitance. The capacitance CL catches a lot of noise, and then the output fluctuations can corrupt the state. Okay, so these are the 4 problems, and some of these problems will become more clear when we look at the solutions. Okay, the first thing that we did is to use a latch. Okay, use a NMOS transistor as a latch. Source, drain, gate. The input is here, the output is over there. That's the clock. So sure enough, my latch has 3 inputs, right? There is a clock, there is input, and there is output. Okay, when the clock value is 1, the MOSFET turns on and the output follows input. So I have a transparent latch. When the clock value is 0, the output should hold on to the previous value because of the capacitance. Okay, that's the idea. And then I pointed 4 problems associated with this. Well, fortunately, we already looked at some solutions to this. Okay, so let's look at the next improvement of this guy. So that will be the design number 2. Okay, the first design was to use just one PMOS transistor, just one NMOS transistor. Okay, and then the second design is more or less familiar to us as well through transmission gate. We look at a transmission gate, which is a parallel combination of NMOS and PMOS. Okay, let us see what problems it solves. Let's look at the first problem. The first problem is that, what was the first problem here? The first problem was that the output does not swing rail to rail. Vout maximum was VDD VTH. Do we still have that problem here?
No.
We do not have that problem here. Rail to rail swing is achieved because V output maximum is going to be VDD, because even though this NMOS is not a good conductor of 1, the PMOS here is going to kick in and act as a very good one and provide the full VDD that I need for a logic 1. Okay, and therefore the first problem is fixed. How about the second problem? What's the second problem? The second problem is that the output is dynamic, okay? Meaning that when the value of the clock, this is clock naught, okay? When the value of clock is 1, then both of these PMOS transistor and the NMOS transistor are on, and there's no problem. When the value of clock is 0, so that's the problem of dynamic circuits. When the clock is 0, okay, then V output is floating. So that problem still persists. When this switch is off, okay, there is no way for me to charge or discharge this output capacitance. It is left floating. Okay, so that's the idea. So the second problem still persists, and the same with third problem as well. The third problem is that the input drives diffusion. So that still persists. The input is still applied on this terminal, which is the source of both the PMOS and NMOS transistors. Therefore, it is still diffusion terminal. So the third problem persists, and so does the fourth problem. Okay, the output state node is exposed. Okay, state node is exposed. Let us see how to solve the third problem now. So we took care of this guy. Okay, we took care of this guy in our second design. So in the third design, I'll try to take care of input driving the diffusion. So what I do is, let's see, the third design of a latch. So I'm showing you the evolution of latches from the ground up. Okay, so let's look at the third design of a latch, which uses something similar to this. Okay, it still uses NMOS in parallel with PMOS. Okay, so that's PMOS. Here is NMOS. One is driven by clock, and the other is driven by clock bar. So this is clock, and this is clock bar. Okay, so here is the input D applied to the source terminal. Here is the output Q, okay? And then let's see, let's say I introduce an inverter, a CMOS inverter. Then the output is going to be Q naught. Then the output is going to be this guy, okay? The output is going to be on that node, okay? So what happens is, what I have solved is, this is called buffering the node X. Let me show you what is happening. The first problem is solved. The first problem is taken care of, rail to rail swing, because I'm using a transmission gate. The second problem is that the input terminal is a diffusion. So I didn't still take care of that because it is still on the source. But the third problem is that noise. The third problem is not solved either. It's what is solved is the fourth problem, okay? That the noise on the output. So fourth problem, if you look at this, the state node is this guy. So let me eliminate all of this, okay? The state node is this guy. That's the state node. That is the output coming from the latch state, okay? Here is the output capacitance that acts as a attracting antenna to accumulate all environmental noise. So because of the inverter that is sitting in between the state node and the output node, what happens is the state node is not exposed. So we solve the second problem as well, because any changes in the output, any noise in the output cannot pass to the state node. The state node is still immune to the environmental output noise. Okay, so this is a fast dynamic noise. And another modification of this is another modification of this is that I'm going to use an inverter, or it is called a buffered input. Okay, I'm going to use an inverter on the input side and not on the output side. Okay, so the output, the fourth problem is going to come back here. The first problem is solved. Rail to rail swing is taken care of because we are using a transmission gate, PMOS in parallel with NMOS. Okay, sure enough, the second problem is that the output is floating, so that still persists. Okay, second problem persists. Okay, the third problem persists here. And who can tell me which of the three and four problems are eliminated here?
The
What's
third problem?
the third problem, and why is that the case?
Because the input no longer drives the drain.
Diffusion. Correct. Correct. The input, which is this guy, is driving the input of an inverter. If you're looking at the input of an inverter, you would find gates, right? Because there's a gate of PMOS up in the pull-up network and gate of NMOS in the pull-down network. So the input is not directly connected to the source terminal of the PMOS and NMOS of the transmission gate. Therefore, this problem has been solved. Third problem has been solved, meaning that the input is buffered. Here, the output is buffered. Okay, so if we use a combination of both of these, then so the fourth problem again persists, because I'm not using an inverter here. If I were to use an inverter here, then I can separate the state node and the output node. Okay, so we are using different techniques so far. And the output, as a matter of fact, is going to be Q naught over here, because the input is inverted over here. Then the output is going to be the inverse of what I would expect. Okay, just like using one inverter here. Inverter plus transmission gate gives a tri-state inverter. Okay, both of these, so both the designs shown in number 3, they're called fast. They're dynamic latches. They're dynamic latches. They're fast. Okay, so those are the designs shown up top. Okay, and they are dynamic owing to the fact that this capacitance is, when the clock value is 0, when the clock is 5, when that clock value is 0, then all of this switch goes away, and independent of what I apply on the input, the output is floating. And for that reason, we call it dynamic logic circuit. Okay, so what we need to do is we need to staticize this latch. Okay, we need to make the latch static. Okay, we need to make the latch static, and that's the fourth design I'm going to show you today. Okay, design number 4. Okay, so far we looked at 3 designs, starting from the simplest one transistor switch acting as a latch. Then I have included a PMOS and NMOS together, which solved one problem number 1 for me. Then I kind of buffered the output, just so the state node and the output node are separated. And then that gave me a lot of immunity to noise on the output side. Now I can do the exact same thing on the input side. That way I can get immunity from the input noise. Okay, so here I don't have immunity from the output noise. Down below, I'm only showing immunity to the output noise. Now what I'm going to do is I'm going to show you some mechanism to staticize the output. Okay, static latches. I'm going to show you what I'm going to show you is called static latch. And it acts like this. Okay, so it's still, the building block is again a transmission gate, NMOS connected to clock, PMOS being driven by a clock knot. Okay, this forms the switch component of it. Now I want to include an inverter here. Okay, I want to include an inverter so that the noise on the output is not feeding back into the input. Okay, but my problem is that this capacitance is leaky. Okay, when the clock value is 0, this switch is off, the transmission gate switch is off, so the output is actually, there is no input on the there is no valid input on the inverter, so the output of the capacitance is floating. Okay, so how do I fix that? Well, I somehow, what I will do is I will take this value, okay, and when this switch is off, when this guy is off, I'll take the value and then read it back, reinforce it, only when this switch is off. Okay, and when this switch is on, this connection should be broken and I should have a pathway that looks like this. Okay, there should be a pathway actually from input all the way to the output when the switch is on. Okay, but when the switch is off, okay, when the switch is 0, then all of this pathway breaks, right? Because this switch is off. So when that transmission gate is off, in that instant, what I want to do is I want to be able to reinforce this value. Okay, reinforce this value somehow. Okay, so if this is a 0, I want the output of this inverter also to be 0. So what I do is I put another inverter in a feedback fashion. Okay, and I apply clocks to the inverter such that this inverter, the one down below, turns on only when clock equals to 0. Okay, when the clock is 0, this switch turns on. So if I charged it to 1, it's going to, this one is going to be inverted to a 0. And that inverter happens to be the, so by the way, when the clock is 1, this switch is off, right? So all of that part of the circuit is off. And then what happens is the value 1 here is going to be reinforced to be a 0, inverted from 0 to a 1 by this inverter. And then it's going to be reinforced over and over again. Okay, that's the idea of a feedback part that is only active for a short duration of time. Okay, only active when this circuit is off. Okay, so here is the transmission gate. Here is the PMOS transistor. When this gate is on, because of the clock here, the feedback circuit doesn't operate. So here is the clock. Here is clock not. Okay, so this inverter here turns on only when the value of clock is 0. Okay, by doing that, this capacitance, the load capacitance CL, is not floating anymore. When clock value equals to 0. Rather, it is reinforcing itself through this back-to-back connected daisy chain of inverters in a back-to-back connected fashion. Okay, so this is called staticization. This is called a staticized latch. Okay, so if I go back to the dynamic versus static, okay, if I go back to the idea of dynamic versus static, I mentioned that in a dynamic logic circuit, there is no feedback, but in a static circuit, there is a feedback. Okay, and because of this feedback, the latch here is called a static latch. Okay, this feedback here through the inverter shown in purple is going to staticize this latch. Okay, so the bucket here that is holding water, it's not, even though it is leaking, it's being, all the leaked water is being fed back into the bucket. So it kind of holds its value. It's not going to leak its charge because of the feedback mechanism. That's the idea by staticizing the latch. Okay, so what we can do is we will, this kind of introduces more problems. Okay, earlier when I had no feedback, okay, when I had no feedback earlier, the noise on the output capacitance CL is isolated from the node Q over here. But because of this feedback, any noise here is going to feed back into this state node here. Okay, and therefore I have reintroduced the problem that has been solved by incorporating this inverter. By buffering using this inverter, I separated the output and this node, state node, but because of the feedback inverter, that sensitivity to noise is reintroduced. So when we come back, what we will do is we will look at a more enhanced version of this latches. So let me not erase that part. So we look at a more enhanced version of the latches that kind of solves all the problems for us. Okay, Questions, please. What questions do you have at this time? Okay, one quick question for you. Is this a buffered input or buffered output?
It's a buffer output.
But
Buffered output, correct, thank you. So this is a buffered output configuration where the output node, it's even though it is buffered because of the feedback, we are feeding the noise back. Okay, all right, we'll come back, we'll stop here and then come back to talk about more enhanced versions in the next class. Questions, please. Any questions before we
Yes,
stop?
Dr. Midori, can you explain again the state node is exposed? Remember the problem?
Yes, I will do that. Why don't I dismiss the class and then before the next class begins, we'll talk about that.